Good morning. As before, we have this beautiful file. Every new slide is prefixed with the slide hashtag, starts with the slide hashtag. A little reminder from the previous lecture, what we talked before. We talked about suspend functions, and under the hood, the suspend function is just transformed from function that accepts n number of parameters to n plus one number of parameters, whereas the last added parameter is just some continuation, right? And again, it's called a continuation passing transformation, which is done automatically by the compiler. Good. We had and have suspend function rules, which say that suspend functions can be called only from other suspend functions. It is a technical restriction because we need to change continuations, right? And if you change arbitrary function for full from non-suspend to suspend function, all the callers have to be marked as suspend as well, and all the callers of those callers and all the callers of those callers, it keeps going. So suspend keyword is infectious. It is poisonous. So it was a little reminder what we talked about in the previous lecture. Now I would like to talk more about continuation. So what is a continuation? First of all, continuation is a concept. It is not a language feature. It is just happens that we have them in Kotlin. We have the class which is called continuation. Continuation is a fundamental concept of evaluation. So to understand it better, let's look at this example. Suppose that we want to evaluate some expression, right? What we do is that at every step, we identify some minimal unit of reduction, we reduce it, and then process further. So here we have 1 plus 2 times 3 plus 4. First of all, we reduce or evaluate 1 plus 2. We reduced 1 plus 2 to 3. Then we reduced 3 plus 4 to 7. 3 times 7 is 21. Perfect, good. Obvious math. And now I will introduce here some framework to think about the evaluation in a slightly different way. At first step, when we identified our small expression which we want to reduce, which we want to evaluate, which was 1 plus 2 in our case, right? What happens is that we split the expression in two parts. We split the expression into one little part, the minimal unit that we're going to reduce right now, and everything else, right? Because we keep the everything else part, and which is the minimal unit that we extracted from this everything else, we will call the place where we extracted from, we'll call it the whole, because we just like unplugged it. And the minimal unit, we will call it a radix. Why we call it a radix? Because it's the part we're going to reduce right now. And so we are reducing the radix, and then we are combining back our two parts, our two pieces, where we had a whole, and we reduced our radix into one expression back again. And that intermediate expression with the whole is called a continuation. Why is it called a continuation? Because it is a statement which we're going to continue to. It is like, it's how we're going to continue to. So continuation is either you can define continuation in different ways. You can say that the continuation is just some kind of context in which the radix is evaluated, right? A continuation is just an expression with a whole. A continuation is the place where radix value is returned to. We reduced it and returned it back to the continuation. It is just a function with a single parameter, because this whole is actually just a parameter, right? So we have the whole expression, just a parameter, and the parameter plugs into the expression. Or another way to think about it is continuation is just the rest of the program. It's everything that's left to do. So we just stopped our execution at some point, evaluation at some point, computation on this slide. We had our expression, we stopped at some point, split it in two pieces. We said that we want to deal only with this piece, but this piece on the right, which is a continuation, it was like the rest of the program. And it was suspended before we could continue evaluating it. It was suspended before we understood how we wanted to reduce the whole. But why care about continuations? Compiler writers care about continuations because they emerge naturally when you write a compiler. when you start thinking about evaluation, sometimes you want to think about continuations explicitly because you want to capture them and hold them like their real values and manipulate with them like with real values. And most programmers don't have much reasons to think about continuations most of the time. Except, let me show you some examples of some programs where you might start thinking about continuations explicitly even as a programmer. So first of all, we have this beautiful function called exitProcess. So again, I'm doing some evaluation. I am concatenating two strings. And instead of the second string, world, I now start using the expression exitProcess. ExitProcess, it accepts some integer and returns nothing. Nothing in Kotlin, hopefully it was in one of the previous lectures, means that the function will never return. So, and nothing can be subtype of anything. So in our case, it acts as a subtype of string, right? And the exitProcess is not the only function which you can play this trick with. So because, well, it is technically an expression. Almost everything in Kotlin is an expression. We try to be a functional programming language. And one of the definitions of functional programming languages is that everything is an expression in such languages. And we almost follow this rule. So if we keep going, we have another function, very popular one, which is error. So error, it also has the very similar definition, but it accepts the message. So it constructs an exception under the hood, throws it, and it says in its signature that it never returns. It stops the execution at some point. Evaluation, you might say. Return, when we are returning something, we're returning the value. But the return statement itself, like the thing that I have selected on the slide right now, it is an expression as well that you can use. And it has type, okay, ID doesn't show it to me because reasons, I don't know, because we didn't support. But under the hood, how does it work? Why can't we write code like this? Why can't we take a string and concatenate it with a return statement, which doesn't make sense? Well, because it's not a statement, it's an expression. And what type does it have? It has a type of nothing. Very similar thing to exitProcess or error. And since return is an expression, you actually can write multiple returns sequentially, which doesn't make sense, and you shouldn't be doing that. And ID highlights it to me and says that it's redundant because the return unit is an expression of its own. We can return it, but it's nothing. Nothing's a type of everything. So whatever return type of your function, we can return. You can keep going, write as many returns as you want to. The same thing about throwing exceptions. The whole expression, the statement of throwing an expression, has the type of nothing. And you can combine them in whatever order. You can do return, throw, whatever. Just a neat trick. So let's think about our beautiful concatenation with the exitProcess in more details in the framework that I introduced before, where we want to evaluate the expression. And first of all, what we do, we split the expression into two parts, into our regex on the right and into a continuation on our left. So we have our whole and the regex exitProcess one. And the question is, how should we reduce it? What exactly should we do with the exitProcess so that the later combination of these two will result in nothing? You can think of it as exitProcess just took its continuation and just threw it away. It didn't use it. It didn't continue the execution. It threw away its continuation. If the exitProcess could materialize continuation, if it could get it as a value, as something that could be materialized, then it could just throw it away and not continue. I'm just writing it in a slightly different format. We had our regex, we had our continuation with the whole, and we reduced it to units. So the reduction rule is that the exitProcess throws away its continuation and reduces to unit. It does nothing. It doesn't continue. Another expression which is interesting to look at from the point of view of the framework that I introduced earlier is the try catch block. We have two statements in the programming language, which is throw in an exception and try catch. Whereas the tries, they have a body, right? And what they do, they try to evaluate the body. And if they don't encounter any throws, then they just return the result of the body, right? But if there are any throws inside the body, Then we evaluate the handler. And throws, it's like a short circuiting operation. When you meet the throw, you stop executing the body. Okay, so just to demonstrate an example, here I'm introducing my own type of exception, which just holds a value inside. I'm introducing my own function of multiplication. Yeah, I'm sorry for that. Then I'm having this beautiful expression where I take 1 and I plus the try-catch expression. So what happens is that we have the expression, then we reduce the try-catch, well, because we see that it will throw, right? This throw is unconditional. It will throw. So we reduce the right part to the header, to the catch body, and we get the 3 times value of the value exception, which is 5. We reduced it one step further. 3 times 5, 15. We got our result 16. Well, let's look at this expression even in more excruciating details. Try to think about it formally, like we did with our framework. So again, we look at the expression. First of all, we need to identify the regex. Where's the regex? What is the minimal bit that we want to reduce right now, that we can collapse and reduce right now? Actually, it is throwing an exception. And how does the continuation look like? The continuation looks like this. It's everything else with the hole inside, right? Good. But then somehow we reduce it to 1 plus multiplication of 3 and 5. So somehow, because before, continuation could be either just continued with the reduced value or the continuation could be thrown away. But here we had one continuation and then it transformed to completely something completely different. So it is actually not clear because some parts of the continuations got preserved. The multiplication of 3 and the exception, it got preserved, but some parts got discarded, like the multiplication of 2 and the whole. So something is going on here. Something is off. That's actually where we have to talk about delimited continuation. And what is a delimited continuation? So let's look at the expression once again. We need to extend our framework because just continuations is not enough. What we deal with right now is called delimited continuation. We move on to the next slide, this one, where my cursor is right now. Actually, this big expression, it can be split into different regexes and continuations, right? Into different parts. We could say that 1 plus something, it is one continuation, right? And it has a hole in it. I will call it hole 2. Well, this hole 2 has a hole inside of it, another hole, right? Which again, I'm writing down here below, which is a multiplication of 2 and some other hole 4. And this hole 4 is actually our regex, right? So we have a structure of some nested holes and continuations. So, well, this second continuation, this second line, it is a hole from the perspective of the first continuation, but at the same time, it is a continuation of its own, right? Because it has a hole of its own. So it is both a continuation and a hole from different perspectives. And as we can see, continuation 1 got preserved, right? It is clearly preserved. But continuation 3 is clearly discarded. And continuation 2 is somehow transformed. Or you can think about this whole try-catch expression as it delimits the discarded continuation 3. So we discarded the continuation 3, but we didn't discard like everything. Like we didn't discard the full rest of the program. We discarded only a small part of it, which was a continuation 2. Sorry, continuation 3. So you can think of it as try-catch delimits the possibilities of our regex. It delimits the discarded continuation 3. Or in other words, the continuation, well, that's actually a mistake, 2 is a delimited continuation. No, actually it was correct. Yeah, because it was discarded. It is a delimited continuation. That's all right. It's the continuation that was discarded. It is delimited continuation. And try catch, the delimiter itself decides to collapse to the catch handler since its body was discarded. So try catch is smart enough to figure out that something weird has happened inside. One of its calls got discarded, so it's just decided to collapse to some other part. Here I attached some additional materials if I got you hooked and you want to learn more about continuations, delimited continuations. I've attached a beautiful talk online on YouTube, which I think explains the idea very well. We will remember this idea of that continuations could be delimited and that there could be some delimiters, like try catch in our case, right? Try catch is a delimiter in our case. And we will just move on to being more practical and talk back about Kotlin. As you remember from the previous lecture, we had this beautiful function which was called run blocking, which blocked the current thread and allowed us to call suspend functions. And when these suspend functions are done, then it would unblock the thread that it blocked before. But if you take a look at the run blocking function, you will notice that it lives in the Kotlin x.coroutines library. So it's not part of the language. It's not part of the standard library. It naturally begs the question, how does it start a suspend function? There should be some real primitive in the language, not in the third-party library, but somewhere in the language that allows you to start suspend function from a non-suspend functions. Now I will reveal to you all the three primitives which actually exist in Kotlin to work with coroutine and suspend functions. The first primitive is the suspend keyword itself. It just means that the function goes through the CPS transformation. The second primitive, it's called start coroutine. And as you can see, it accepts as an extension parameter, it accepts a suspend function. And as a normal parameter, it accepts a completion. And so what this function does, it allows you to call suspend function in a callback style. Once the suspend function is done, the completion, which is actually just a callback, right, which is just a fancy name for a callback, as we discussed in the previous lecture, is going to be called. Once the suspend function is done, the callback is going to be called. So start coroutine function allows you to call suspend function in a callback style. And you have a suspend coroutine function, which we talked about briefly in the previous lecture. Now, when we have more knowledge about the continuations, halts, redexes, reduction rules, evaluations, the concept, now, hopefully this sentence makes sense to you. And the sentence is suspend coroutine, the function, when you call it, it becomes the expression, it becomes a redex that decides what to do with its continuation. So you take the expression, you split it into redex, which is suspend coroutine, and the rest of the continuation. And suspend coroutine allows you to materialize, because if you look at the suspend coroutine definition, you will see that it accepts a lambda, and that lambda is going to be executed. You will get continuation, access to the continuation. You will materialize it, and you will have a possibility to decide what to do with it. Everything else, like Kotlin X coroutines library, for example, can be implemented on top of these three primitives: suspend keyword, how to call a suspend function in a callback style, and a way to suspend your computation, suspend, quote unquote, do something with the continuation, and then resume or not resume. Well, just like suspend function, suspend coroutine decides. The lambda that you pass to the suspend coroutine decides. Let's play with it a bit. So here I have this beautiful code. So what it does, I have the foo function, I have the bar function, I have the bus function. So what does the foo function do? It takes its continuation and it just resumes it. So actually, it just does nothing. And if we try to call the foo function in a callback style, well, we need to pass a callback. I won't talk about empty coroutine context here. Just ignore this part. But the important part here is that this lambda. So actually, this continuation acts as a lambda, which is going to be called once this foo function is done. And it is done immediately. So what we have on the standard output of this program is that it prints done1 on the main thread, and it prints done2 on the main thread. So these two lines are just executed sequentially. Okay, another function bar. What it does is that it continues it resumes its continuation on some other thread. It starts the thread, resumes its continuation there. So what does the bar print? It turns out that done3, when we start bar in a callback style and pass a callback here, it turns out that the done3, it will print as you can see down below, it will print bar, which is the name of the thread, right? We called it bar. It means, well, since we continued our continuation on some other thread, the callback, which signals to us that we are done, it is executed on that thread naturally. And you can also see that the done3 and done4 are swapped. So first we see done4 on our standard output, and then we see done3 on our standard output. It means that, well, it is because when we suspended our coroutine and started our computation on some other thread, the previous thread, the main thread, it got released, it got nothing to do, so it just popped out, exited the stack frame from the third coroutine function, and just continued its execution to this line, and printed done4 on the standard output. That's what happened. That is what happened. Okay, and then we have our beautiful bust function, which takes its continuation and it just does nothing. And it does nothing. It throws its continuation away. So we have done, and when we start the bust function in a callback style, we see that the done5, our callback, it is never printed. It is not there. But the done6 is printed because, well, we exited the start coroutine function and then we just continued our execution. So what we notice of all of these examples is that start coroutine, it delimits suspend coroutine. What it means, well, remember our delimited continuations that I discussed before, is that because when we discarded our continuation in the bus function, right, we didn't discard the done6. So it's actually not like continuation is not the rest of the program until the end. It is the rest of the program until the start coroutine. Start coroutine delimits what we can capture, the point that we can capture until 2, continuation until 2. We captured our continuation until the start coroutine. Start coroutine is the delimiter. The delimiter is also a place where we return to when we suspend. What does it mean to suspend? If we don't call continuation.resume immediately on the same thread inside the suspend coroutine lambda, it means that we suspend. For instance, here in the bar function, we suspended because we didn't call continuation immediately, we called it on some other thread. So in a sense, from the main thread perspective, we threw the continuation away, we just shelved it, stashed it somewhere, and executed somewhere else later on some other thread. That's what we did conceptually. The same thing about buzz. So the bar function, it actually suspended. The buzz function, it actually suspended as well, because it didn't continue its continuation immediately on the same thread. The foo function, it actually didn't suspend, because this operation is a no-op. You could just replace it with the unit, and then the IDE would helpfully tell you that the suspend keyword is redundant. So the foo function didn't suspend, but the bar and buzz functions, they both suspended. Okay, good. Now we learned that start coroutine delimits suspend coroutine. Start coroutine is our delimiter. Besides start coroutine function, there are some other functions in the standard library. They are called start coroutine intercepted or return. They are create coroutine or create coroutine unintercepted. But they all have the same expressive power. All they do is they convert your suspend function either to callback passing functions, to explicit callback passing functions, or they just directly call them. So they all have the same expressive power, and for all intents and purposes, they do the same thing. And the same thing about the suspend coroutine function. Besides the suspend coroutine function, there is suspend coroutine unintercepted or return. But again, these two functions, they have the same expressive power, and for all intents and purposes, they do the same thing. Okay, enough talking. Let's actually implement our, for example, exitProcess function, right? Because before I promised to you that if exitPromise could somehow materialize its continuation and manipulate with it directly, we could implement exitProcess. So let's do that. Unfortunately, we cannot actually exit until the rest of the program because we don't have the unlimited continuations, which can capture continuation until the very rest of the program. We only have delimited continuation, and our delimiter is always a start coroutine because we need to jump from a non-suspend world to suspend world where we have the suspend keyword because of the code coloring problem, as we discussed in the previous lecture. So what I have here is that I have my exitProcess function, which tries to mimic the behavior of exitProcess. And what did I tell you before? I told you that the exitProcess function, what it does, it just throws its continuation away. That is exactly what happens here. It just takes its continuation and throws it away. But we need to write some helper to our delimiter that will just start a coroutine. So what is signature? What is the signature of this function? It is non-suspend, but it accepts a suspend block, right? And notice that the T, it is not nullable, but well, we just return the T, which is got returned internally by the block, but this one is not nullable. But the return type of the function itself, run delimited exitProcess, is nullable. Why so? Because if this thing inside the block, it exits abnormally, it doesn't finish normally. We don't have the result of T, right? So that's why we will return null in this case. Okay, good. So what happens here is that we take our block and we start it, we run it, we call it, that block, that function, in a callback style. And in our callback, inside our callback, what we do is that, well, inside the callback, so let's actually take a look at the continuation definition. So it's an interface in the Kotlin Coroutines package. So it is inside the standard library. Remember how before one of the definitions of the continuation was that it is a function that accepts one parameter. That's your beautiful parameter. So it accepts a result, has this one function, and when we resume the continuation, when we tell it to continue, we can resume it with two values. We can either resume with the normal result.success, like for example, we have these beautiful helper functions here, or we can resume it with an exception. So we do result.failure and resume it with an exception. And as you remember before, what I told you, one of the definitions of the continuation, it is either a callback. Here's your beautiful callback. It's just one function inside, right? Don't ignore this context property. It is there. It is here. Well, as you noticed, so far we have been passing, where is my file? We have been passing this empty coroutine context, so we don't care about this bit right now. We have the context property, which we ignore. So essentially, the significant and important bit is this function. So it is a callback. Here's how you call your callback. It's just a function that accepts some result and returns unit. Okay, good. Now, when we understood better what a continuation is, we get back to our exitProcess example. And when we start our suspend function in a callback style, we get access to it has a type of result. So we either get a value of it or we throw an exception. So it will just propagate and we just record the result in a variable. And here on this line, what happens is that, oh no, I didn't want to scroll anywhere. What happens is that if the callback was executed, it means that the block didn't suspend. And if it didn't suspend, we will just get our value and we will return it from the run delimited exit process, which is propagated. But so yeah, if we didn't suspend, then the lambda callback is executed, then we capture the result, then we just propagated it. But if the callback wasn't executed, it means that the block, the suspend functions, was suspended. It means that the myExitProcess function was called, which threw the continuation away, and we didn't execute this callback. So we will return null. And well, here I just write some examples of the usages. For example, like we have here, we run our delimited exit process and we print something, we exit, and we print something after. And we have before one and after one. And as you can see, the standard output of our program is just before one. We don't have the after one. The same thing here, where we have some kind of recursion. So, and somewhere deep inside our stack, so as you can see, it just recursively calls itself until it reaches 5. And when it reaches 5, it calls the whole call stack. It exits the process. So, and it doesn't have, and it won't have an opportunity to print, to finish all these recursions, right? And that is exactly what happens at these examples. So we will see the before 2 printed here. And we will see a bunch of before recursion printed on our standard output. 5 to be precise. Here, our 5 before recursion printed on the standard output. But we don't see the after one, we don't see the after recursion on our standard output. Because the execution was killed. It was stopped, it was suspended and never resumed. And another example with the try finally block. As you might know, we use, maybe learned already, we use try finally. What does finally say? It guarantees you that the finally block will always execute, and it is an opportunity for you to close some resources. So for example, if you open files here on this line, you can close them later, right? Well, unfortunately, it is a lie if you're using suspend functions, because if it just doesn't continue its continuation, you will never get an opportunity to call the finally block. And that is exactly what happens in this code snippet. We will see open resource on our standard output, but not the close resource, unfortunately. So that's why you have to be careful. Throwing an exception, just throwing an exception away is considered an anti-pattern. In Kotlin specifically in Kotlin, it's considered an anti-pattern. There's nothing wrong with throwing out continuations in general in theory, but in Kotlin, it's considered an anti-pattern specifically because of this code example. Here we are throwing out continuation for educational purposes. Before I told you that try-catch can be implemented with continuation, with the concept of continuation. So let's try to do that. Let's try to mimic the throw and the try-catch. So what happens here is that I introduce our suspend function throw. I have the function try, which has a body, and it has a catch block. The body is a suspend block where we can call our throw function because it's also suspend. And what happens here is that, well, if you think about it, our try is a delimiter again, because it is the point where we decide what happens if, because what does the throw do? It discards the inner continuation of the try. It only discards the body continuation. It doesn't discard until the very end of the program. It only discards this bit. And then the try block, the delimiter, when it sees whether the continuation was discarded or not, it decides what to do further. Well, if the continuation was discarded, it will decide to call the catch block. So since it's a delimiter, we're using the delimiter operation, which is a start coroutine. When you start thinking in these terms, the delimiter, the continuation, well, yeah, when you introduce the concept of delimiters, every time you understand that something is a delimiter, that's the place where you should call your start coroutine function. That's where you should use this primitive. So what happens inside the try? So it starts the body, it passes the lambda, and again, if this lambda is executed, it means that if this callback is executed, it means that the continuation wasn't thrown away. We resumed normally. But if the lambda wasn't executed, that means that we abnormally finished our execution. We just discarded the continuation. So that's exactly what happens here. We have some result. So if it null, it means that this lambda wasn't called. It means that the continuation was thrown away. We complete abnormally. That's why we need to call the catch statement. Great. But if the result is not null, if it's a success, it means that the body was returned normally, and then means that we just need to get the value out of result and just return it. That is exactly what we do here. And if result is a failure, it means that some real exception was thrown from the body. And well, for now, we just forbid it because it's just odd to throw real exceptions from. We're trying to mimic try catch, and real exceptions get in our way, so we just forbid them. And yeah, and this statement is just unreachable because we have considered all the cases. So, and how does it look like? It looks like this. So we have our try and we have our catch. As we can see here, we don't throw. That means that it will print try and no catch. No catch won't be printed. This line won't be printed because we don't have any throws inside. If we have a try, we can throw, and we don't have to throw immediately from here. We can throw somewhere deep in the call stack, but this whole call stack has to be marked with the suspend keyword because suspend keyword is poisonous. And if we, so what this snippet prints, it will print throw from somewhere in the call stack, then it will throw, and it will go to catch because it threw, right? And then it will print end. And this example, it will just crash our program because we try to throw a real exception from our try catch, which try to mimic the try catch, the built-in try catch construct of the language. Okay, good. Once again, I just mentioned a warning that specifically Kotlin, we consider just throwing away a continuation is considered an anti-pattern because you can accidentally leak finally blocks, as I showed you before, and we do that only for educational purposes. Okay, it turns out that actually, like almost all control flow operations, control flow statements like throwing, like returning, exiting, or breaking and continue in loops, they also could be implemented via continuations. And here I give you a homework to mimic the while loop yourself. As you can see, we have some kind of while context, and you had the DSL lecture before, right? So it is like a small DSL here because it's a receiver. And so inside this lambda, not only you can call suspend operations because it is a suspend lambda, it is a suspend functional type, but also you have the access to these functions because your function has the extension receiver, which is called while context. And so how do the invocation look like? Here we have a normal while loop. So we have the variable a, we while indefinitely while true, but once a reaches 5, we break. So on your standard output, you will see something like iteration 1, 2, 3, 4, 5, right? That's the expected output of this first program. The expected output of the second program, well, iteration A, typo, iteration B. Here I have the B, and I again iterate. What happens here is that, well, this while loop is limited by 7, so we definitely won't print more than 7 iterations. But at the same time, when we have the 5, we continue. So it means that we won't have an opportunity. We just go to the next cycle, so we won't have an opportunity to call these 2 lines. which means that this break, it won't have an opportunity because it happens at the very same condition. It won't have an opportunity to be called. That's why we will see all the 7 iterations. It will have 1, 2, 3, 4, 5, 6, 7, right? Except when it's 5, we may 1, 2, 3. Yeah, we just miss the 5. We see all the 4 iterations, but there's like 4. Then we jump to 6, but then we continue to 7. If we throw an exception from the while loop, we expect that it will be propagated through the while loop and will be caught later. Or we can also combine our while loop, the one that we created, we suspend with the continuations, and the normal while loop that we have in the language. And remember how you need to use labels when you have the nested loops and you need to break from the inner loop, you want to break out of the outer loop, right? Here's the same thing. This break, it won't break from this loop from this inner while loop, right? This break will break from the outer while loop because this magical function has no power over this while keyword. Yeah, like these two are connected. And these two are connected. So it's like we invented another way to break out of the inner loop. Yay! Congratulations. So normally, if we didn't have these break statements, what would it print? It would just go over 10 iterations from in the outer loop. It will go over 10 iterations in the inner loop, and it would just print a matrix, right? Because yeah, like 0, 0, like here below, 0, 0, 0, 1, 0, 2, 0, 5. And then we continue horizontally until 0, 9, and we continue vertically because here we have our rows, row 0, row 1, row 2, row 3, and we would continue down to row 9, but we broke on the row 3, right? We only printed 3 rows and 5 columns. That's the expected output of these, not a complete matrix. We stripped it on both sides. And if you're done with this homework, there's like an additional one, a slightly harder version. What if we wanted to write this while loop to this? Well, what if we wanted to replace this nested while loop with our beautiful while loop that we introduced before? So again, the homework here is that you have some to-dos in the implementation that you need to fill in, and to mimic the break and while functions of the programming language. But in this case, the break function, it can also accept a loop label. And where does it get the loop label object from? It gets it from the while. So when the while starts its execution, its cycle, it gives you a label, and you can use that label to break out of the outer loop here. And here you're just breaking from the inner loop. Okay, so now when we packed with this powerful knowledge of continuation, suspend keyword, 2 magical functions, which are called, one of them start coroutine, another suspend coroutine. If I ask you, what does a suspend keyword mean in Kotlin? There are 2 answers. If you're a normal, pragmatic Kotlin developer, suspend keyword for you means that the function supports non-blocking style of programming, the async style of programming. But if you're a scientist, it means that the function will go through the CPS transformation, which is just a syntax sugar on top of the callbacks, as we discussed before. I'm just reminding you the details. Remember how we talked about virtual threads in the previous lecture? Actually, it turns out that the underlying mechanism of virtual threads is continuations as well. So if you look into the implementation of the Java, you will find that they have this beautiful class, which is called continuation, and it's located in the JDK internal VM package. So it is actually a private API. And what does this program do? So it creates a scope. It doesn't matter, some kind of API. We create a continuation here. We bring before the yield. We have the continuation.yield, which accepts the scope, and we have the after yield. And when we constructed our continuation, we bring something before our first run. We run our continuation, then it will yield it will temporarily stop its execution. Then we will print something between runs. Then we'll continue its execution. And so it will continue its execution from the yield statement till the end of this continuation. So while creating this continuation acts as a delimiter, yielding acts as suspending, where you suspend and you throw your continuation away. And then in the end, we will see after the second run. So you can write this program in Java. You will have to use these magical flags in the CLI to acknowledge that you use some internal Java APIs which are not meant to be public, and well, it will print what it will print on the standard output as I described it right now. And an arbitrary blocking Java API, if they want to support virtual threads, what they need to do is that they need to check if the current thread is the virtual, and then they have a special logic for it. So for example, for instance, we have the thread class and we had the thread.sleep call, right? And what it did internally, it called sleep nanos. And what sleep nanos does is that it checks if the current thread is the virtual thread. And well, inside it does some magic. Well, not actually magic. Eventually, it will call this API. It will call continuation.yield inside. And that's exactly how these blocking quote-unquote APIs, because they are no longer blocking if you call them on virtual threads. That's how in Java they support non-blocking style. But the disappointing part of all of this is that, in Java specifically, is that both languages, Java and Kotlin, both of them, they have continuations. But continuation API in Kotlin, as we saw before, it's an open API for everyone. And you can use it. You can abuse it to create your own language constructs like break, continue. These break and continue look almost like language concepts. And you just, well, implemented these language constructs all by yourself. And not only that, you can also implement the Kotlin Coroutines library, the asynchronous way of programming. That's what an open continuation API gives you to, as a Kotlin programmer, you get this, you get this benefit. And virtual threads in Java, they also implemented on top of the idea of continuations. But unfortunately, continuations API in Java, it is a private API. And because of that, since nobody has access to this API, virtual threads are implemented in the Java standard library. So it's not a separate library, but it's baked into the language. Well, it's like a trade-off of how much power you want to give to user. Kotlin decides to give more power to users. It gives them more trust. So to summarize, we had these async programming solutions that we discussed. We had the futures, like a box that promises you to return some value. We have the suspend functions, which now we discussed in all possible details. Hopefully you understand this beautiful concept. And we discussed virtual threads, which is a Java answer to suspend keyword. But yeah, well, one benefit, quote unquote, that they have is that they are the virtual threads. They don't have the code coloring problem, unlike suspend functions, because suspend functions, they are implemented on the compiler level. So it's just a syntactic sugar on top of your functions. We do some automatic transformation on your functions, the CPS transformation. And virtual threads, it is a virtual machine language feature. So that's why it doesn't introduce the code coloring problem. And actually, Kotlin coroutines and virtual threads, they are, well, yeah, like that's exactly what I just said, that they are hard to compare because, like I said, virtual threads, they don't introduce the code coloring problem. And there's this famous the article which argues that that's a nasty problem that programmers do not want to deal with. But some other programming languages, they argue that having suspension points in compile time can be beneficial, because when you have suspension points in compile time, you know statically which of your functions can suspend, and that can help you to prevent some concurrency bugs. You can, well, if you're interested, you can read this document, these links that I attached here. So now we go to one last topic of this lecture, which is sequences. So what is a sequence? Sequence is an interface in the Kotlin standard library. It is defined like this. So it is located in the Kotlin.sequences package. It's an interface with just one function, an iterator, which returns just an iterator. You can notice that the interface sequence looks very similar to the interface iterable because they have the same definition. It's just we in Kotlin declared our own sequence because the idea of sequences, it is a Kotlin way to build lazy computed collections. Iterable doesn't give you this guarantee, sequence does. So it's just an informal contract between these two classes. And conversely, Kotlin list and Kotlin collections, they are not lazy collections, they are eager collections. So I will tell you more what lazy and eager mean in more details just a bit later. Let's look at how we can build a sequence. And turns out that we will be using suspend functions again, because the sequence, it can be one another application besides all the applications that I mentioned before. Another application of the continuations is lazy sequences, or sometimes in other programming languages they are referred as generators. For example, in Python they are known as generator, and in Python they also have the yield, but it's not a function in a library. It is a keyword in Python, and in Kotlin it is just a function because, well, we have this beautiful concept of continuations as the first class citizen concept in the language, which you can just materialize and use it directly in some way. Yeah, so we have this beautiful function sequence in standard library, but actually, just to mention, it is in standard library for convenience. You could implement sequences as a third-party library, but it just happens that implementing a sequence is a very easy task. Is not, well, Coroutines library, it's a huge library. It's like, it is tremendously huge. It is gigantic. That's why it's implemented as a third-party library. We don't want to put it into standard library because this way it's very hard to maintain. So we want them decoupled. But sequences, it's a very small part of the. It's not a big library. It's compared to Coroutines, it's a very tiny piece, and it's very useful. So that's why we put it in the standard library. But it could live as a separate library. And for example, if you don't like something about sequences that we ship with the Kotlin, you could create your own version of sequences as a third-party library. In the standard library, we have this function, which is called sequence. It accepts a suspend lambda with a receiver. And this receiver is what allows you to call this yield function, because this yield function, if you navigate to it, it is actually located in the sequence scope, right? And the sequence returns the sequence. So what happens here, we created a sequence, we printed before, yielding some result, then we printed something again, then we yielded again, and then we printed something after. And this sequence, it is like a lazy infinite collections of elements, not necessarily infinite, but it can be theoretically infinite, and I'll show you just in a bit. So here it is finite. It just has two elements inside, and when we iterate over this sequence, what happens is that it prints before, then it prints 1 from this side because we printed 1. Then we go to the other cycle. We will unsuspend from here. When we yielded a result, we suspended our execution here. Then we unsuspended when we asked for another value in the for loop, and we printed between, and then we will print the second element because it got yielded. Then it suspends, and then we'll print after. Okay, maybe, well, I will discuss it in more details how it works just a bit later, but hopefully you can already grasp how it works in your head. Like I mentioned, sequences they are lazy. So for example, if I could create an infinite sequence of Fibonacci numbers. So I have 1, 1, I yield 1, 1. Then I, in the infinite while loop, keep summing up the two previous elements, yield another element, and just shift the previous and the before previous elements to have access to them. For example, the 21 is a Fibonacci number. If I try to iterate over this sequence, this would be an infinite loop. So I have to manually break at some point. 21 is one of the Fibonacci numbers. Or, for example, I could use the take operator, which just takes the first 6 elements. I promised to you that I would tell you how the sequence works, to discuss it a bit, how it works, how it interrupts with the continuations. So the delimiter for sequences, because we remember how the sequence looks like. It returns an iterator, and this iterator has 2 functions inside. It has next function, and it has the next function to get the next element. So the delimiter for sequences is the hasNext and .next function. It's the place where we return to when we suspend, and we suspend when we call the yield function. So you can think about the sequences in this way. So somebody calls the .next call, right? The .next starts the coroutine. We start coroutine because it's the delimiter. The coroutine at some point will call the yield function. The yield will call suspend coroutine. It will suspend. And what happens inside is that we stash the continuation inside the sequence object. We stash the value that was passed to the yield class. And since we suspended here, we didn't resume our continuation directly. We stashed it, but didn't suspend it yet. We return to the delimiter, to the .next, and the .next just returns the stashed value that was passed to the yield call. Next time somebody calls .next, we will just resume the stashed continuation. I see that I'm running out of time. Actually, that there are not a lot of things to discuss. I will start the next lecture by finishing these tiny bits about sequences. We're going to talk about Jetpack Compose and mobile development on Android. And a little spoiler, we'll briefly talk about continuations again, because Jetpack Compose is a powerful framework. It's a compiler plugin which is implemented on top of the idea which could be described as continuations as well again. That is it for today.